we have Javier Fullea, and Federico Munch will be introducing him.
So, hi everyone. So actually, Javier is a great example of career mobility because so he did his bachelor's at the Universidad Complutense de Madrid. Then he did his PhD, a master's and PhD in Barcelona, and then he moved to Ireland for postdocs and a senior researcher at the Institute of Advanced Studies. And now he's back at the Universidad Complutense de Madrid as a senior researcher. So he did sort of a very nice full circle. And so essentially his research focuses on combining different types of geophysical data, such as heat flow, surface elevation, gravity data, and seismic waves, with petrological information, essentially mineral physics and thermodynamics, to determine how temperature and composition changes in the Earth's interior. And he specializes mostly on the lithosphere and uppermost mantle. And he worked both on a global scale and regional scales. And I think today he's gonna talk about his most recent results on a global scale, right? I hope, otherwise I'm saying bananas. So Javier, the stage is yours.
Okay, thank you very much, Federico. Well, good evening to everyone. As it was mentioned, it is 1 a.m., so I hope you're a bit fresher than me. So thank you very much for giving me the chance to present my work in this seminar. For me, that's a great opportunity of, like promoting a bit the work that we've been doing recently. So today, my talk is focused on, upper mantle thermochemical imaging, if you want, using a couple geophysical-petrological approach, basically an inversion of both terrestrial, and by terrestrial I essentially mean seismic tomography, plus other things, but mostly seismic tomography, and satellite data. Satellite data essentially is gravity, but I'll mention just very briefly at the end something about magnetics too. So this is part of the work that I've been doing in the last 4 or 5 years. Part of it as funded by European Space Agency project called 3D Earth. This was one of the products, the new upper mantle model, lithospheric model that I'm going to be presenting you now. So when it comes to imaging the Earth, of course, there is always this fundamental question: how to best combine all the different data sets that are out there for us to interpret, and that regardless of the scale, global, regional, doesn't really matter. So for instance, if you look at, say, tomography data, you probably are looking at seismic velocity models or anomaly models. I guess in Berkeley, you know a lot about that, of different kinds, body waves, surface waves, normal modes, and so on. But there are also other ways of imaging the Earth. For instance, if you take gravity data, for instance, satellite gravity data, you probably can invert that or mold that for density structure at some level, upper mantle, lower mantle, crust, depending on the wavelengths that you're looking at. And there's also information, say, from petrology, from mineral physics, mantle analysis, that gives us, another perspective to the problem. So how do we combine those things in the best possible way? How to integrate this information? There are different ways of doing that, of course. When we first started with this project with ESA, we decided to use something that we had been developing for the last 10, 12 years, what we call integrated geophysical-petrological approach, modeling approach. This essentially means that if you, say, for instance, take seismic data, rather than inverting or modeling that for velocity anomalies or gravity anomalies, if you model that for densities, we rather want to parameterize that in terms of some more fundamental parameters. For instance, temperature and composition of rocks that actually bring together all those secondary physical properties like elastic moduli or seismic velocities, densities, or electrical conductivities, if we would be talking about magnetic data. So the way we do that is that we use some basically petrological software that tell us, solving thermodynamic equilibrium problem, what will be the stable mineral assemblage that we should expect for a given temperature, pressure, depth, and composition in a broad sense? What minerals would be stable, what the compositions of the minerals would be, and these sort of things, out of which we can compute elastic moduli, seismic velocities, densities, which are the properties of interest here. So basically, we're solving at the same time typical geophysical problems like wave propagation or electromagnetic or gravity integration, and at the same time some thermodynamic problem. And the model that I'm showing you here basically is constrained by satellite gravity. It's an ESA-funded project, so it has to be satellite, of course. There is tomography, in particular surface wave tomography. I'll come to that in a minute. There is a sense of isostasy. We know that on average, the Earth should be isostatically compensated for the long wavelengths, and we want to introduce that information. And there are other sources that we can use, for instance, measures of surface heat flow. So why integrated geophysical-petrological modeling? Well, one of the things about this sort of modeling is that once you start introducing things like thermal modeling or compositional information, these sort of things, you kind of narrow down the uncertainties inherent to seismic, for instance, or general geophysical inversions. So if you take this figure here on top right, those are sea wave velocity profiles from surface wave tomography model Sheffer-Lebedev. And you can see that for different terrains, what the slopes are. There's a lot of variability there. And for instance, once you start introducing temperature modeling and composition, like we did, for instance, in this example in Mongolia, you can see that we go from the gray area, which basically shows the range of possible seismic velocity models that fit equally well the seismic data, dispersion curve in this case, Rayleigh fundamental mode. And when we introduce our extra information, we can narrow down this to the red and the blue lines, right? So we kind of reduce that significantly. There's another question that often comes across when we're dealing with transforming a tomography model into a gravity model, right? So if we change velocity anomalies into density anomalies somehow, and then we compute the gravity field, typically it happens that we get amplitudes for the geode, for instance, or Fourier anomalies that they're larger than what we would expect. So there's a problem with these two, and we'd like to have this also, solved somehow. So the new model that I'm presenting here is called WINTERC-G. That stands for waveform and gravity inversion for temperature and composition. It's basically constrained, as I said, surface wave tomography primarily, and also gravity data. How do we do that, right? Because we had some previous experience with this sort of integrated geophysical-petrological modeling at regional scales, but the challenge here was to make it at a global scale. So we split basically the inversion to make it tractable into 2 steps. And we do that following 2 criteria, basically. One is the dimensionality of the data, and the other thing is the sensitivity of the data. In the first step, we deal with data that to a good approximation can be modeled as 1D. For instance, if you take dispersion curves for Rayleigh or Love waves, this would be sensitive to the local shear wave velocity and density and P wave velocity beneath that point. Or isostacy as a measure of the lithospheric buoyancy can be, and it's actually calculated for 1D columns, or surface heat flow measuring the slope of the geotherm close to the surface of the Earth. Also, these data sets are fundamentally dependent on the temperature structure. This is the driving parameter. And then in the second step, which is coupled to the first one, we introduce the gravity field. And the gravity field, of course, has to be modeled in 3D. And in this case, we are sensing the density structure, crustal density structure, but also in our parameterization, mantle composition, because mantle composition is what controls with temperature the density in our model. And we have these 2 steps coupled using prior information for one into the other. And that within a thermodynamic framework where the key parameters, densities and seismic velocities, are computed based on temperature and composition. And depth, of course. for the data, the background model is a global waveform tomography produced by basically Sergei Lebedev's group. You can see that we're using well, basically all broadband data available for publicly available repositories. And on that, we apply an inversion of surface wave and S-wave waveforms, altogether 1.25 million approximately seismograms over 5,000 stations, which is a considerably large data set, and which means that we can do things like outlier removal, therefore keeping only the most mutually consistent data. So out of this, rather than going directly to standard 3D, the 3D tomographic inversion, 3D distribution of velocity anomalies, shear-wave velocity anomalies, we go on the side a bit, and then we compute phase velocity maps for Rayleigh and love waves from the mantle mode. You have an example of the data that we're using here at 40 seconds and 75 seconds. And for a comparison here, you can see a previous phase velocity map that's for, I guess, Rayleigh. So once you do that for enough number of periods, right, you can take a location in the Earth and sample that for periods and construct a dispersion curve like this one here, right? And this is what we really put into the inversion. We really inverting fundamental mode, Rayleigh and love dispersion curves at each location in our model in this first step that I mentioned before. So altogether we have 12,500 1D columns that translates into about 230 kilometers lateral resolution. And the other fundamental data set that we're introducing into the inversion is satellite gravity data. So here in particular, we used a global Earth model, geopotential model, XGM 2016, which of course uses ESA's satellite data, of course, because that's an ESA-funded project. And but not only that, also previous missions too. And well, we use the geode anomaly, and here you have a total geode anomaly zone. But we have to filter that, and I'll mention something about that in a minute. The geode anomaly we use to constrain the upper mantle density or the upper mantle composition, the way we parameterize things. Whereas gravity gradients, right, and gravity gradients were measured on board satellite for the first time within ESA's GOTS mission. This is now a tensor. So we have six independent components, right? The trace of the tensor is vertical, north, north, east, east, and vertical north, vertical east, and east, north components. And because of the height at which these gradients are measured, we have actually very good sensitivity of the crustal density of the structure, moho, and shallow most mantle, really. So we use it for that part of the model. This is a typical 1D column in the first step inversion. Remember, surface wave tomography plus surface heat flow plus topography that we are trying to reproduce at this stage. On the left column, you can see a typical, well, not very typical, actually, it's quite thin, but a mantle geotherm. And the most important parameter here, that's the lithosphere, thermal lithosphere, defined, the base of which is defined by, a particular isotherm here, which marks this kink in the geotherm. That for us is 1300 Celsius. Then below that, we invert for a buffer, thermal buffer zone of variable thickness. And then below that, we get into, the zone where convection is strong enough. And then we have something close to an adiabatic gradient, which we characterize with 3 different nodes. Remember, our model goes from the surface down to 400 kilometers, it's an upper mantle model. Then we have the crust, that's the blue line, that will be the moho depth in this particular column, and 3 layers, the crustal layers, for which we define seismic velocities, particularly VS, but also densities. And we've got, in terms of composition, the lithosphere and the sublithospheric mantle. I'll come back to that because here you see it's just expressed in terms of aluminum oxide content. I'll come back to that. And because we do invert Rayleigh and Love dispersion curves, we can invert for radial anisotropy. I'm not showing that here, but we do have a radial anisotropy model as well. Okay, so that's how the inversion setting looks like for step 1.
Sorry, can I ask you a question?
Yep, sure.
How because you're modeling heat flow, right? So then,
Oh yes,
and that doesn't that involve assuming a thermal conductivity, basically?
Yes. We computed from the slope of the geothermal and the thermal conductivity of the shallowmost crustal layer. And yes, yeah, of course, there is you need to parameterize also thermal conductivity and heat production for a crust, and the same for the mantle. Yes.
So does that depend on your location? So if you're in, for example, the thermal conductivity is different if you're in the oceans or the continents, or are you assuming the same?
Yes. It's different. We have basically a bimodal model, and there's an oceanic model and a continental model. But for continents and oceans, we don't differentiate. It's just this ocean versus continents that we have. Yep.
Thanks.
Yeah, thank you. And so I was mentioning compositional parameterization, and here in the mantle. So rather than using 5 or 6 major oxides that typically characterize the mantle composition, which would be a bit hard sometimes in terms of global scale inversion, what we do instead is to use prior information from global data sets from xenoliths and periodotite massifs, like those plots that you see here. That, for instance, is calcium oxide versus aluminum oxide, and this other plot here would be magnesium oxide versus aluminum oxide. So there are trends, right? And we can exploit these trends to reduce the complexity of the compositional space. And in fact, from our tests, we found that we could reduce, the parameters in terms of composition to 2: aluminum oxide and iron oxide, the ferrous one. And in fact, for the model that I'm showing you here is just aluminum oxide, because iron oxide we keep constant. So this way of parameterizing the chemical space, in a way, you can think of it as a melting trend, in a way. Like if you start from what we think is the primordial mantle composition in the lithosphere, so we're here, this is aluminum oxide, magnesium oxide plot, and you start melting, you move along this trend, right? So you start removing aluminum oxide and reaching in magnesium oxide and reducing calcium, right? The way we are using aluminum oxide as a proxy to depletion or how refractory our composition is, right? Another way of looking at this is to think of it as a system similar to the pyrrolite model, where we have variable amounts of hasbrogitic refractory components and basalt fertile components in different proportions. Okay, before I go into step 2, let me just mention something about the sensitivity analysis, why we can split step 1 and step 2. So here, what I'm showing you are physical property derivatives computed using Perplex and thermochemical software at this pressure, 7.6 gigapascals, and for this iron oxide composition. And so on the left column, you can see the density variation, right? Density variations in the mantle of this depth versus composition in the top plot, and the bottom plot is density variations versus temperature. And on the right column, what you see is variations for VP and VS, shear wave, P wave velocities with composition top plot and temperature bottom plot. So let's say that we have good information about the temperature from the inversion of the surface wave data, right? So we have the step 1 already in place, and then we want to adjust the gravity field. How do we do that? Well, let's say that we have to change in 15 kilograms per cubic meter the model at some depth. You can do that by either changing, if you look at this plot here, your composition, and remember it's aluminum oxide, but aluminum oxide controls the other oxides too, in 1 weight %. That gives you your 15 kilograms per cubic meter, and that translates in the velocities, if you look at the linear part of the plot, in about 0.2 percentage. If you do the same with temperature, your 15 kilograms per cubic meter, then you're going to need about 200 Kelvin change for that. But 200 Kelvin translates into about 2% change in sea wave velocity, and that's a lot. What this means is that for the same density variation, the associated thermally induced variation in Vs is about 10 to 12 times larger than the composition.W, which effectively means that if you have a good constraint on the temperature from your seismic data, you can adjust the gravity modifying the composition without destroying considerably or at all, basically, the feed that you have already. You can, and in fact, you can do this back and forth to get some converging solution if you want. This is what I was trying to say here. Just you're looking at the residuals for all the model, right? So statistically accumulated residuals at these different periods for Rayleigh here on the left plot and for Love on the right plot, and the brackets, so the dispersion globally. The black brackets show you what is the residual for step 1 inversion. And then the red brackets show you how much we deteriorate the model by changing the composition, the crustal density in step 2 in order to fit the gravity. So you can see that it's actually not a big change. And and that's just one step, if you do back and forth step 1 and step 2, you can actually reduce even more the size of the red brackets. So inversion 2, as I said, now we have 3D gravity data we want to invert in a way regularized by the temperature distribution from step 1 that we use as prior information. And then our variables here would be the composition in the mantle, described by aluminum oxide, as I mentioned, and then that in the lithosphere and the lithosphere, and the crustal density. And this is what I was trying to illustrate at full depth, at any depth. If you know the temperature from the step 1, and you have the composition, that is your variable, you can predict the density, and the density is what you need to tune in order to match the gravity field. For the gravity,
can I ask us one more silly question?
Go.
So is your inversion linear? Is it probabilistic? So what kind of, is it deterministic inversion?
No, the second step, it's a very simple linearized inversion, locally looking at the misfit between predicted and calculated value, and then correcting based on that, an iterative solver, but a very simple one actually.
But that's for step 2, or
for step 2,
step 1.
Yeah. No, step 1 is Lavenberg-Marquardt inversion, nonlinear gradient search. And this other step is because it's 3D. In order to make it simple, it's a much, mathematically is much more simpler, yeah. But it still works. I can tell you that. Okay. So I was mentioning, for the geode anomaly, or generally for the gravity field, so far what we're doing in our model is to match the total signal, total gravity signal, minus degree 2 and 3, harmonic degrees 2 and 3, which correspond to basically more longitude or wavelengths of more than 12,000 kilometers. This we can do because we know relatively well that those harmonics are related to lower mantle and CMB signals. So we don't want to model because we are dealing with the upper mantle. But it's not so straightforward to how to filter. For instance, if you look at the sensitivity kernels on the right plot, what people do is to basically retain the signal from degree 9 or 10 onwards, right? So smaller wavelengths, and it's clear from the kernels that this will work. But it's also clear if you look at the lower harmonics that this gray zone, degrees 4 to 9, they contain signal in the upper mantle too, right? So if you don't include that signal, if you remove that signal, you're removing part of your upper mantle structure too. So there's actually no unique solution to this filtering problem unless you work with the whole Earth. But I'll come back to that. So for uncertainties, something that we can do is to compute the covariance matrix, the posterior covariant matrix out of the inversion, and this is for step 1. Gives you an idea of the uncertainty that you should expect from the data sensitivity at least. Here I'm showing you on the left the LAB, lithosphere-asthenosphere boundary depth, the best result parameter in inversion step 1, where you can see that it's pretty well resolved in general. And what we see is that once we go deeper, because of the surface wave, the nature of the surface waves, we start losing resolution. And for instance, as an example of parameter that is less well resolved, and so when you hear temperature at the bottom of our model, 400 kilometers, that's the least well resolved. And well, in some areas is not very good, but in general, it's acceptable, right? It's still acceptable. We can do the same for step 2. And in here, the covariance matrix is actually much computationally demanding. So what we do is to compute it at a quarter model resolution, basically 20 degrees. That's why the plots here look rather blocky, but we keep the full resolution at the observational grid. And these are the two main parameters after step 2, the average crustal density, where you can see that we resolve better, of course, the continental crust, because it's thicker than the oceanic counterpart, and it contains more signal that we can model gravity-wise. And on the right, you can see the whole lithospheric and lithospheric mantle composition, where it's actually the opposite, where we can resolve better the oceanic mantle than the continental mantle. So this is how
Sorry,
the model.
can we?
Yep.
Just one more question. Can we go back one more slide?
Oh, yeah.
So, because your uncertainty stays seem larger, like if you look at the Andes, for example, where you have the subduction zone, right?
Yeah.
So, why didn't have an idea why this might be? Is it because your geometry is not 1D?
Possibly, yeah. I mean, the subduction zones are. We do see something about subduction zones. I will show you temperature maps, but some of the things are not so clearly visible. It basically means that basically you can in those areas on the left plot you can change the LAB and you don't have that much sensitivity from the dispersion curve, either because it's more noisy or because our parameterization represents less well the reality and therefore is unable to cope with what we have there in the Andes, for instance. There are different reasons. I think it depends. We would have to look point by point to try and understand what's going on really. But from top of my head, this is what I think it's probably the case. At least when we look at the residuals from the dispersion maps, these are usually higher. The misfits are usually higher below on top of subduction zones and active zones than in the terrain. So probably yes. Yeah.
Thanks.
It should be okay.
I have a question or comment on that. I think were you saying that the elevation was, you were assuming that it would be isostatic? Because perhaps in these regions, like the Andes or subduction zones.
Absolutely, yeah. No, you're absolutely right. This is a perfect comment, but I'll mention that as well. We, in principle, ask for isostasy, but we don't fully enforce it. That in fact is not the case in subduction zones. I will show you a residual isostatic map in a few slides that will hopefully help me explaining my point. But yeah. No, of course we cannot reproduce topography in a subduction zone or even in zones where dynamic topography it's expected to contribute as well. You will see that.
Thank you.
Maybe continue. Okay, that's the model. Some of the model parameters anyway. That's the Moho depth here, where we use as prior information crust 1.0, and then we let that vary within statistically determined uncertainties based on the coverage, on the data coverage of crust 1.0. On the right, so that there are changes actually. You probably don't see it so clearly here, but in fact there are changes with respect to crust 1.0 in Africa and South America that are not small actually. The lithospheric composition, lithospheric thickness, thermal lithospheric thickness. Remember, this is the best result parameter And here, of course, you can see cratons sticking out the skull, thick, some of them, with differences in structure. In oceans, the scale is not great here, but I'll show you something on oceans. We do see some patterns that are interesting too. On the bottom plots, you can see composition. The left plot is lithospheric composition, and this is basically constrained from the surface wave dispersion curves, but also this isostatic here, it contributes as well. And you can see that the cratons are more refractory. Remember, aluminum oxide is a proxy for depletion or fertility in our model. So the higher the aluminum oxide content, the more fertile the mantle, and the other way around. And on the right bottom plot, you can see the sublithospheric composition in terms of aluminum oxide. And here, actually, this map is constrained essentially by the gravity data that we have little sensitivity from the tomography here. And it's actually quite different from the lithospheric maps. Some of the patterns, for instance, it's interesting, you can see that the oceans are quite different. I mentioned that also in the next slide, but basically you can see the Pacific is more refractory than the Atlantic and the Indian Oceans, and this has consequences in terms of the density distribution. If you look at the lithospheric composition, here is for reference the global petrological database for different terrains. We can plot that in a different way. We can group by lithospheric thickness, that's for continents in red, so aluminum oxide content in the lithosphere versus lithospheric thickness, and that's the same for oceans. And you can see that we do see some trend of decreasing fertility once we go to deeper lithospheres, so more cratonic lithospheres, as one would expect, although there's considerable dispersion. And in oceans, close to the mid-oceanic ridges, composition is more refractory, as one would expect. Then when you increase the age of the oceanic lithosphere, the thickness, thermal thickness, you increase the fertility, and there's a maximum at something 80, 90 kilometers, and then it flattens or even decreases a bit. That probably reflects, we think, the predominant lithospheric age that is hit by plumes and refertilized. Those are temperature maps. Mostly it's a lithosphere at different depths, 100 kilometers to 60, 330, 400 kilometers. And for comparison, you have main hotspots, diamonds, main tectonic plates, boundaries of them. So you can see mantle plumes or hotspots are warm in general, as one would expect. Also interesting to note how craters actually remain cold in our model down to the top of the transition zone. It's not always the case in tomography models. So how can we also can we assess the robustness of this inversion temperature-wise? Something that we can do is compare with independent information. For instance, thermobarometric data from mantle senolytes in cratonic terrains. So here you have 4 examples: Siberia here, Slave Craton, Cadval Craton, and Adelaide folded belt or Gawler Craton. The red line is the geotherm from WINTERC, from our model, and the black dots represent depth or pressure and temperature estimates from the senolytes. And you can see that in general, at least for 200 kilometers, we have a reasonably good agreement. For deeper depths, not so clear, maybe reflecting thermal processes that affected the senolytes, but that could have been relaxed by now. In Cadval, if you look at these 2 lines, these are senolytes erupted, I think 90 and 120 million years ago. They represent a much colder paleogeotherm than what we see nowadays. We think this probably reflects the more recent activity from the African superplume. And similarly, in the Adelaide folded belt, the dots correspond to Adelaide actually. The present day geotherm that we see is actually hotter, but it corresponds very well to the present day Gawler Craton geotherm. So what we think is that possibly at the time of the eruption of the senolytes, the folded belt was thermally the same as the adjacent gold crater. So all in all, it works reasonably well. Now, just you probably have heard about the ongoing volcanic eruption in La Palma in the Canary Islands. So these pictures, these photos here are from the last weeks. It's quite active, and this is the island here, La Palma, and you can see the lava flow here. Here, actually, it's actually somewhere in the south part of the volcano. The active volcano is somewhere here, and the lava flow is flowing westwards, and it's actually creating this new chunk of coast, if you want. So I decided to quickly have a look at the model at the scale of the Canary Islands to see if we could see something interesting there. And that's what we got, right? So these are temperature sizes at 400, 330 to 60 to 100, 150 and 100 kilometers, 110. So if we start from the top of the transition zone, we can see that would be the regional effect of the North Atlantic plume, but then there are these two cold blobs, northeast and southwest of the islands. This is the same, still 330 kilometers, but then it changes, it starts changing at 260, where we start to see that the cold anomaly moves towards the eastern islands and the African margin, right? And here is very clear at 200 kilometers. There is this structure here, this cold structure that actually creates a divide between the west and active islands. That's La Palma here, the one with eruption, but also El Hierro was active 10 years ago, something like that. Whereas the eastern islands are less active or non-active, except for Lanzarote, actually. And then here still a bit, and then here just 110 kilometers, you basically seeing the margin structure. But it's interesting that, at all depths, La Palma is always within the hot mantle region, and this divide, at least in between 150 and 260 or a bit more, which creates like kind of a stopover for the heat, possibly coming from the plume that we see on the rest of the island chain, which I think is at least interesting to mention. Now, coming back to oceanic lithosphere, something else that we can do is to to group by age, right? So here I'm plotting depth of thermal lithosphere, so basically the depth of our 1300 Celsius isotherm for all the model, for all the oceans, right? With age versus magnetic determined age. And the brackets show the dispersion, basically, and the black points represent the base of our buffer zone, the 1400 Celsius isotherm in our case. So basically below here, everything would be convective. That on top of the red dots, we would have the conductive lithosphere. So it looks like we have cooling from mid-oceanic reaches down to 100 million years, and then some flattening. But what happens if we disaggregate this into the different main oceans? That's what you have here in this plot. The red line for the Pacific, the blue line for the Atlantic, and the green line for the Indian Ocean. And you can see that then we have cooling all the way down to the oldest lithosphere, with some changes here in the Indian Ocean, but the trend is of continuous cooling, not cooling as you would expect in a half space model, but neither like in a flattening plate model. It kind of keeps on going, but smoothly or linearly. And it also, there are differences, like the Pacific is warmer at all ages than the other one, so it cools less quickly than in the other oceans. And then on the right-hand plot, we have predicted surface heat flow and the data also with dispersion. Remember that our model tries to match the surface heat flow as well. And we do reproduce well the pattern of surface heat flow in oceanic lithosphere with age, with the exception of the vicinity of the mid-oceanic reaches, where we don't get, of course, very high values that could be rated to melt and transient effects. We don't have that in the model, but otherwise it's actually doing a pretty good job in reproducing the surface heat flow measurements. Another thing that we can look at is mid-oceanic ridges, right? So we know that we have slow spreading ridges like in the Atlantic that are deep, have this normal fault architecture, and then we have fast spreading ridges like the Pacific East Rise, where we have more like a dome structure and they're shallower. Compositionally, there are also differences, at least based on mid-oceanic ridges, basalts, and in terms of temperature as well, right? So this is what this plot tries to show, that for different spreading rates on the horizontal axis, the actual ridge depth, decreases with a spreading rate up to 60 millimeters per year, something like that, and then it flattens. So can we say something about that from our model? If we take a stripe of less than 20 million years around mid-oceanic ridges, and then we bin that in boxes of 10 millimeters per year in terms of spreading rate, we get plots like that. So here you have the lithospheric composition in terms of aluminum oxide versus spreading rate. We do see a trend, right? When we have slow spreading rates, the composition is more fertile, and fertility decreases up to 50, 60 millimeters per year spreading rate, and then flattens. For temperature, we also see a trend, and it's reversed. In this case, slow spreading ridges are colder than faster ones, and we have this trend of increasing temperature up to 50 millimeters per year, and then kind of flattens. And the density, in this case at 260 kilometers, but in general in the sublithosphere, is a combination of the temperature and the composition in our model. And again, we see that slow spreading ridges are denser than faster spreading ridges, at least up to 50, 60 millimeters per year, where things are not that much related to density. What we think is they're both thermal and compositional effects that relate to ridge push, at least up to 40 or 50 millimeters per year, and all things slab pull or other forces taking place take over. But possibly in terms of the buoyancy of this range of spreading rates, the structure beneath the ridge plays a role, and a role in the way that slow spreading ridges are more fertile, and they're colder than their faster counterparts. This is what I was mentioning about isostasy. We, in principle, ask for isostasy, but we don't completely enforce it. And in fact, this map is proof of it. This is an isostatic residual topography map from WINTER. It means it's the prediction that our model makes based on the average crust lithospheric density minus the real surface elevation. The red areas are zones where our prediction for topography, isostatic topography, is below the real topography or bathymetry, and blue is the other way around. And you can see that, as I was mentioning, subduction zones are generally blue. That means that the prediction from our model is on top of the real topography, which means that you would need something pulling down to compensate and get the real topography. And on the other side, you would have red zones like here in the North Atlantic, where the prediction is from our model is below the real bathymetry. And that means that you would need some supplementary dynamic contribution pushing up your topography to the real value. In fact, when we compare this with oceanic models based on lithospheric age and corrected by sediment and crustal loading, we have a pretty good match, and these are totally independent from our model. In continents, things are different, but this is partially because the crustal density and the crustal geometry is way less well constrained, and this plays a major role in the determination of an isostatic model. But in the future, what we're doing is to try to combine this with proper dynamic estimates of the Stokes flow problem. And that's for the gravity filtering. Don't want to really, because I think I'm running for too long. But basically, if we alternatively, rather than removing just degree 2.3, we remove degree 2.9, right? An alternative winter model would look like something like that. And if you subtract these two, you get something like this, right? So this is the difference between the two modes, adjusting different parts of the gravity field. And this signal is not immediately obvious if it belongs to the upper mantle, to the transition zone, or to the lower mantle, or to parts of a combination of those, right? So this is something that we're trying to figure out, how to best combine upper mantle and lower mantle models to consistently model the full signal, the full gravity signal. Finally, because WINTERC is a temperature and compositional model, and because we can use laboratory experiments constraining electrical conductivity of the major upper mantle minerals, melt and water, we can construct, and we indeed have done it, connectivity map based on WINTERC. It looks like something like this, different depths. This is a recent work published in JGI as well. I'm part of this too. And what is interesting is that when you look at, and I promise I mentioned something about magnetic data, and I'm doing it now. If you look at the spectrum, for instance, of the time average oceanic M2 tidal magnetic field, this is a part of the magnetic field that is sensitive to the upper mantle resistivity, electrical resistivity of conductivity structure. What you see, right, is that WINTERC-based models actually predict something that is well within the ranges predicted by specifically tailored models to match the magnetic data, in this case from swarm mission, right? The dashed line would be to specifically design, the model is specifically designed to match the magnetic data. And the solid lines are WINTERC end member models. And it's remarkable that regardless there's absolutely no magnetic information at all in WINTERC, still it's able to make a good job in predicting the first order, the one-disk conductivity structure of the upper mantle. And it opens new possibilities. For instance, now what we're trying to do is to integrate this in 3D. You know, if we can plug in the magnetic information to constrain all the things that we're not so sensitive in our model, like the amount of water or refine our melt distribution. We have a melt distribution as well, didn't show it, but we do have it. And these are some of the things that we're doing. And with this, I finish. These are basically my conclusions. I'm not gonna go through them. You can read, but basically the take-home message is that there's a new global thermochemical model out there constrained by surface wave, state-of-the-art surface wave tomography, data plus gravity plus heat flow with isostasy. This is published in JEI. If you're interested in, like having a look at the model, or whatever, commenting or analyze or whatever, there are 3D thermal compositional DPVS density fields available in this link here. And just my final comment, with ISA, we produced some outreach video on the model that you can find in this other link here. And that, for kids and for non-specialists, maybe somehow fancy if you want to have a look. And that's all. Thank you very much for your attention.
Thanks very much, Javier, for your talk. We have time for questions.
Yep.
I have a question. Is that okay? Thanks for the talk, Javier. And the tidal ocean M2 fit is really cool. I was just wondering, do you have that figure where you discuss trade-offs with temperature and density? And I was just wondering, do you include anelastic effects?
You mean attenuation?
Yeah.
Yes. Yeah, of course, yes. I didn't mention that, but so basically we use Perplex, this petrological software to predict anharmonic velocities at any point in the model, but then we have to correct that for anelasticity. That's based on, we have the standard models based on the temperature, on the grain size, on the reference period, and the amount of melt. And in fact, yeah, it changes a lot. It decreases a lot the wave velocity, particularly for first. Yeah.
So it's kind of just giving people who don't think about this an idea of all the kinds of things you have to consider, as you mentioned, grain size, all this stuff to make those corrections.
Yeah, of course, which includes more more freedom that you have to change things, but it has to be done. Otherwise, you cannot really reproduce the data.
Thank you.
Roland?
Yeah, thanks for that talk. That was fascinating. So for those of us who are interested in the rheology, mechanical properties of the upper mantle, does your model provide the opportunity to do better with trying to constrain that from these kind of information, given that you incorporate compositional, thermal, etc. variations that usually we don't have, right? We just say, oh, VP, VS is this, and this gives me a viscosity, but this should do better. Yeah,
we've done a few things along the lines of that. For instance, in North America for GIA studies, it's part of the future work. Of course, your point is perfect because we have the temperature and a composition. We could at least try and estimate a 3D viscosity model of the upper mantle, and that's the next step, the natural next step. Of course, there are things like grain size that are not going to be very well constrained, but
of course
we can at least put some end members there in place. And I think it's very interesting, and it links to what I said about, a natural continuation of our modeling is, okay, we can predict some residual isostatic topography that actually is in good agreement, at least in oceans, with other things. But can we make it compatible with, a convection model with the rheology of the lithosphere that is on top of that, the lithospheric lid, that is, blocking or not blocking whatever density anomalies are below. This is the next step, and I think it won't be automatically clear that the upper because first of all we don't have the lower mantle model, but even if we assume decoupled convection model, we still need to. My feeling is that we won't get straight away something compatible. We will have to tune things. We will have to re-invert based on the information from the dynamic modeling too. This is going to bring information. For instance, there's a clear trade-off with the crustal density structure. This is not very well constrained. Crustal density at global scale, I mean. There's a lot of room to vary that. For instance, I have a new density model, but I'm not claiming that that's a definitive one. I know that it's going to be trading off with other things. And one of the things would be, for instance, dynamic topography. There's an interplay between dynamic topography and whatever you assume in the crust. But yeah, I think it's great. And the next step definitely is going along the lines of computing a 3D viscosity model. There's someone here in Madrid that it's going to be working on that in this kind of dynamic problems, using a promising technique, actually numerically effective to solve the Stokes problem. Yeah, thank you.
Thank you. That sounds great.
I know you didn't show this, but because you said that you have melt in your model, right?
There is, yes.
So does the melt estimates that you get make sense with what we know? Do you have more melt at mid-ocean ridges, for example, or hotspots, or?
In general, I have a plot here included supplementary. Let me go there. But keep in mind, it's written there pseudo melt, not like proper melt, because we somehow, modeling melt with surface waves is a complicated business, because whenever you start adding the information from mineral physics, right? Not mineral physics, sorry, from experiments measuring the effect on the elastic moduli and the velocities of melt, then you get, dramatic drops. But dramatic drops and surface waves are not very good friends, right? Because you can have a very narrow zone with a very steep decrease in the shear wave velocity, and the surface wave is not, the dispersion curve is not going to see it. So in order to alleviate this problem a bit, we did some kind of adjustments, basically trying to introduce, pre-melting effects, that we know that when we are at a fraction of the solidus, the experiments, most recent experiments tell us that we start to see a decrease in the velocities even before there is melt in the system. And we included that in a very simple and crude linear way. That's why what we're seeing in those maps is basically an estimate. I wouldn't take it as as an estimate of the content, absolute melt content, but an idea of where the melt is going to be in depth. Not maybe the amount of melt necessarily, but yes, I think, well, the fact that we see it in these regions, I think it makes sense, and it's not very far from other models, right? Basically, these zones are where the lowest velocity really in a tomography model would be located, in this depth range and in these areas. And this, I think, is well constrained. The absolute amount of melt, I don't think so, because that trades off with a lot of things, and we cannot really constrain that very well with only surface waves. If for instance, we were modeling electromagnetic data of some sort, like magnetic data or EM or magnetotheorics that would go deep enough, yes, in that case, yes, because the amount of melt, then I think it will be better constrained. But with the data that we used here, I don't think so.
All right, thank you very much, Javier. I really appreciate your giving your talk. All right, well, thanks again.
Thank you very much.
Bye.
Thank you very much. That was great.